Today we're going to look at several different types of graphics in the media. A multiple bar graph has two or more sets of bars that allow comparison between two or more data sets. All the data sets must involve the same categories so that they can be displayed on the same graph. So it's a bar graph, but there's more than one bar. You could have a multiple line chart. So there's more than one set of dots and lines. Or you could have a stack plot, in where there's a vertical or horizontal stack in bars or lines. So we'll look at some examples so you'll know what I mean here. Example 1. Here is a multiple bar graph because we have two bars for each section. So we have the median annual earnings of full-time workers, ages 25 and up, by education and gender. So what this is asking us to do is, what are some general messages revealed by these graphs? What do you see? Okay, so what's one group that makes more money? If you have a professional degree, right? So you could say the higher your degree, the more money you're going to make. Now, that's not been so much the case for me. I've got a master's and I don't make that. Anyway, community college professors, for the most part, no. What other observation could we make? Men make more than women. Still. Even if they have the same degree, men make more than women. Even with the same degree. So another graph here we're going to look at. So here's unemployment rates among individuals 25 and older by educational level. Okay? So the purple is they didn't graduate high school. The blue is they graduated high school. The green, they had some college or an associate's. And orange, they have a bachelor's degree or higher. So what can we say? Well, we could say that unemployment rates are lower for higher educated people, right? No, this isn't set in stone, of course, but on average. So here's a stack plot. Stack plots can be a little bit hard to read. So here's what this is saying. If we look at this first bar, okay, it says average estimated undergraduate budgets for full-time students. So this is saying that a full-time student in a community college, 2-year commuter, okay, will they have these expenses? That little over 3,000 of their expenses will be tuition and fees. You can see the blue down here. About a little over 7,400 will be room and board. And then there's $1,229 to spend on other expenses. $1,648 on books and supplies. Notice at the end there is this number 15,584. That is the total. If you were to add up 3131, 7419, 1229, and so forth, you would get a total of 15,584. So if you wanted to ask a student how much do they spend on tuition and fees and room and board, you could add these two and get approximately $10,000. Okay, so that's how it's read. Here's another example of a stack plot. It says, what was the death rate for cardiovascular disease in 1980? Well, it kind of tells us, but let's talk about this here and what's happening in this graph. Make sure. Okay, making sure there wasn't more to it. So this bottom down here, the purple, is cancer. So what can we say about cancer rates? Well, they've gone up. And we could make some conclusions about why, but we won't go there. Then you can see tuberculosis is in the blue. So here's the deal here. In the year 1960, how many tuberculosis cases were there? We can't say that there were just under 200. That's not the case. You have to look at the total span. There's almost zero there. So in 1920, how many tuberculosis cases were there? So right at 100 to maybe 225. So maybe 125. We would subtract 225 minus 100. You see what I'm saying? So when we're looking at the death rate for cardiovascular disease in 1980, you look at 620 minus 180. And there were 440 deaths per 100,000 of cardiovascular disease in 1980. Okay? Graphs of geographical data. We're often interested in geographical patterns in data. Like in this case, we've got energy use or oil use for different states. So the blue uses the most oil, and the orange uses the least. Not total, but per person. That's the big deal there. So the energy used per person. We'll come back to that. So part A of example 3 asks us what geographical characteristics are common to states with the lowest energy use per person. The lowest energy use per person is the orange. So that's Florida, New York, New Hampshire, Maine, Rhode Island, Connecticut. Am I getting all these right? I think so. Plus Arizona and California. Okay, so let's list these. California, Arizona, New York. Let's talk about these one at a time, actually. So there's New York, New Hampshire, Maine, Rhode Island, and Connecticut. Why might they, well, it doesn't really ask why. What's the geographical characteristics? That would be northeastern states. But we could think about why. Well, those states are most populated. And they may, so there's more people, and so the energy rate per person would be lower because there's so many people. California and Arizona, same thing. There's a lot of people, and Florida too. All these states are heavily populated. All are pretty heavily populated or in concentration anyway. Okay? And you could go back and talk about why do these use the most? Well, Alaska, it's cold, so yeah, they're using a lot of oil, and there's not a lot of people. Wyoming, there's not a lot of people, so you're spreading out that energy use per person. And then the second one says, were there any temperatures above 80 degrees in the United States on this figure? Okay, so looking at this figure here, we have, you see this a lot, you watch the weather on TV. We have temperatures across the United States. Up here, we've got temperatures in the 20s. This light blue is in the 30s. The light tan is in the 40s. Yellow is in the 50s. Orange in the 60s. Pink is in the 70s here and down here. And then the purple was in the 80s. So the answer to our question would be southern parts of Florida were above 80 degrees. And last but not least, sometimes you'll, well, no, this isn't last, I don't think. Anyway, sometimes you'll look at three-dimensional graphs. And they're a little bit harder to read. Here's a picture of a three-dimensional graph. So in a three-dimensional graph, we're able to have three axes, not just the vertical and horizontal, but vertical, horizontal, and a depth. So example 4 says, based on this figure, about when did China surpass Russia in total carbon dioxide emissions? So if we look at this, we want to line things up. And when you go, like if we're looking at the carbon dioxide emissions of India in 2010, you're not going to do this, okay? You have to, my recording stopped, parallel to here. So we'd have to go, let's see, can I get this close? Looks like about 2 billions of metric tons of carbon dioxide emissions was in India in 2010, okay? While if you look at China in 2010, oops, you want to go from the middle of your little bar. And then we got to go down here, about 6.5 tons. So it asks us, when did China surpass Russia? So Russia is the light blue, and China is the yellow. So here, Russia is more than China. Here, China is more than Russia. So somewhere between 1990 and 1995, China surpassed Russia in carbon dioxide emissions. A few cautions about graphs. There can be perceptual distortions. We'll look at some examples of that. Actually, here's one. This is showing you the value of $1 comparing 1980, 1990, and 2005. So if the value of $1 was $1 in 1980, in 1990 it was only really worth 63 cents. But look at this. Look at how much smaller does that look. That looks. 63% would be more like, I don't know, this much of it or something, okay? And that's much bigger than this. So it makes it look unrealistically smaller. And the same thing, 42%. How is that 42%? Okay, so think about things being unrealistic. Watch the scales. So in this picture, both of these show the exact same thing. Women as a percentage of all college students. In the first picture, it looks like the percentage of women as college students greatly declined around 1950 and greatly rose in the year 2000, right? Big decrease, big increase. But in this graph, yeah, it declines, but not hugely. It's fairly consistent, between 40 and 60 really percent. Not a huge difference like this graph looks. So depending on what the people want you to see, if they're talking about, if it's a women's advocate group saying that, in the 50s, then they would want to look at the first graph. While if it's a men advocates group, they will look at the second or something like that. Okay. So think about the scales. And why do they look so different? Because this one is going from 30 to 60, and this one is going from 0 to 100. So depending on what you're looking at, one might be better representative than the other. But the 0 to 100 is a little more relative. Percentage change is in graphs. Let's see, do we have a picture of this? No. Graphs that show percentage change can be misleading unless you interpret them with great care. So sometimes the percentages in the graphs look bigger than they should be or smaller than they should be. And pictographs are graphs that are embellished with artwork that make things misleading. So if we look at this, we've got these little people all over the place, and we've got a globe and all kinds of things making this look weird. And it's talking about the world population in billions of people. Well, this looks pretty dang linear, doesn't it? From 1804 to 2054, we've risen consistently. Nope. Look at the intervals. That's over 100 years there, people. That's only about 30. That's only 14. 13. 12. 14 again. Okay? Because these the intervals aren't the same, you can't say that this was a linear growth. It is exponential, by the way. But whoever drew this graph wanted it to look linear. And that concludes the section.